Hi everyone. Welcome to today's lesson. So today we're going to be looking at integration by parts. And one of the first things I want you to do is to recall the product rule for differentiation that we learned back in Calc 1. Now, that product rule says that if we want to differentiate the product of two different functions, if we want to differentiate a function that's made up of a product of two functions, then what we have to do is take the derivative of the first function, multiply it by the second function, add that to the first function multiplied by the derivative of the second function. And since products and addition are since multiplication is commutative under addition, we can rewrite that in any way that we'd like, so long as we keep the terms together, in this case f of x times g prime of x plus f of x times g of x. So looking at this and identifying that we will need this whole process, one of the motivating factors is if we were to try to integrate this particular question, or this particular integral, which was x times e to the power of 2x dx. If we try to integrate this particular integral, you're going to see that substitution won't exactly do the trick here, which means substitution fails and we are limited within our realm of integration as to what we can do. And therefore, this new technique arises where we want to use the product rule. So how does the product rule come about? Or how does the integration by parts come about when we're talking about the product rule? So one of the first things that we then want to do is I want to keep using this formula that we've already developed from the product rule. And I'm going to keep using this formula, and I'm going to modify this formula just a little bit. Okay, here we are. Now let's go ahead, let's change the color here. Perfect. Okay, so once I have this formula that I am working with, what I'm going to do at this point in time is I'm going to integrate both sides. So I'm going to integrate this formula. My apologies, I'm just copying and pasting here. It helps because I don't want to write this over and over and over again. There we are. And let's remove this. There we are, looking good. Okay, now let's go ahead and let's modify the colors here. And so I just want to make sure that the colors are modified to the colors that we're working with here. That way nothing is too out of sync. Okay, there we go. That's good enough for now. Okay, so what I'm doing here is I'm integrating both sides of this equation, and I'm integrating using my integral with respect to dx. Now, when this happens, you're going to see that on the left-hand side of this equation, we're really applying the fundamental theorem of calculus. So the fundamental theorem of calculus, again, if we're taking the integral of an antiderivative, then that means they are inverse operations of one another, and hence we will get this result back, which is just f of x times g of x. Now, on the right-hand side, it's a little bit more complex than that. On the right-hand side, we actually just distribute the integral into each individual term, which means we're going to have f of x times g prime of x dx, and then we're also going to have the integral of f prime of x multiplied by g of x dx. And in this particular instance, we want to then isolate one of these values. Okay, now simply because looking at the integration by parts formula, this integration by parts formula says if we have a product of two functions where one of those functions is a derivative, then we will be able to solve. And so if I isolate this very first function here, so let's say that I have f of x times g of x minus the second term, which is the integral of f prime of x times g of x dx. This is going to equal to the integral of f of x times g prime of x dx, as such. And if you notice, this is your actual integration by parts formula, the one that we have listed at the top right-hand side of your screen. And again, this integration by parts formula says that if we want to take the integral of a function that's being multiplied by a derivative of another function, then we can do it so long as we decompose the functions into f of x and its appropriate antiderivative. So this is what we want to observe as we start moving forward, or as we start progressing through the course. We again want to make sure that we're able to identify what is the initial function that we're working with. I'm typically going to call that your function u, and what is the, in this case, differential dv, which we're going to call g prime of x dx. If we can identify those two pieces, then naturally, working through this integration by parts, we should be able to extract or evaluate these individual integrals. So jumping straight into that process, we want to now evaluate these integrals. So evaluate the integral. Part A is going to be the integral of the quantity of x minus 1 times sine of pi times x dx. Now again, you're going to see that if you try to do substitution, substitution will fail. In that instance, we then go into integration by parts. So moving into integration by parts, again, I'm going to find what is my u and what is my dv. Essentially, what I'm working with, I scrolled up just a little bit for my integration by parts formula using the differentials. This is my preferred method. So this is my preferred method as to how we want to use this integration by parts. And it's my preferred method simply because, oops, my apologies, simply because what we have here is that we can identify the individual functions without ever actually having to go into f of x, g of x, f prime of x, s g of x, so on and so forth. So I want to identify what is my u and what is my dv. And notice, if you notice right up above that, that's exactly what I did. I identified u and I identified dv. And as soon as we do that, then the integration by parts formula turns into the formula of u times v minus the integral of v du. And you're going to hear me say that a lot. Anytime I'm working with the integration by parts, I need u times v minus the integral of v du. So if you ever come to my office hours and you hear me whispering that when I'm doing my integration, it's because that's the way my mind is piecing all of this together. And there will be an integration by parts formula for definite integrals when we have those bounds that we'll get to in a little bit once we start analyzing and working with those specific definite integrals. For now, let's keep going with the question. I'm going to identify my u as x minus 1, and I'm going to identify my dv as sine of pi times x dx. So again, these are the first two substitutions, or these first two parts that you then have to identify. Always identify u and always identify dv. remember that when you identify the value for u, or the function for u, you will have to then take the derivative of that. So when you identify u, remember we're taking the derivative. When we identify the differential dv, which is sine of pi x dx, we're going to have to take an antiderivative of that differential. So if you cannot take a derivative because it's too difficult for the u value that you chose, we might have chosen, or you might have chosen, the wrong u value. If you cannot integrate your dv, in other words your differential, again, it should signify that we probably made a mistake somewhere, that we chose that value incorrectly. So now that we have this, let's go through and let's identify what du is going to be. So in this particular case, let's see, du will then just be the derivative of x with respect to x, and that's going to be 1, so that's just dx. Okay, that's not too bad. And then dv, we're going to have to find the antiderivative for sine of pi x. So what's the derivative of sine of pi x? Well, in order to find that, we basically integrate sine of pi x, which means we'll be left with 1 over pi times, or let's actually make this negative, negative 1 over pi times cosine of pi times x. Now again, once we chose that dv, we would have to integrate, or in this case, find the antiderivative. As such. All right. So once we have this, then we can go through and we can set up our integral. The integral that we were initially looking at, that was the integral of x minus 1 multiplied by sine of pi x dx. Well, this now separates into the integral of u, or sorry, this now separates into u times v minus the integral of v du. And what you're going to see me do a lot is this, is that I want to now take u times v, and then I'm going to subtract it by the integral of v du. So here we go, u times v, so that's going to be x minus 1 times negative 1 over pi times cosine of pi x minus the integral of v du. So the integral of v is going to be integral of negative 1 over pi times cosine of pi x times du, in this case it's dx. And again, here is your u, here is your v. So again, u times v minus the integral of v, and then that dx is that du. So again, we get that formula for this integration by parts, which is again always going to be the integral, it's always going to be u times v minus the integral of v du. And now we can just go through that integration process to finish evaluating this. So for this first term, I just have my x minus 1 multiplied by, all right, let's actually simplify this a little bit more. So negative 1 over pi multiplied by x minus 1 multiplied by cosine of pi times x. Negative and negative, because it's negative factors, that's going to be a plus. I now have to integrate cosine of pi x. Integrating cosine of pi x should get me 1 over pi squared multiplied by sine of pi times x. Okay, that's not too bad. And then we have plus c, because this is an indefinite integral. So we have plus a constant. And now look at this. We've actually evaluated this. We've actually integrated that initial integral, which was the quantity of x minus 1 multiplied by sine of pi x. So again, this is what we now have, and this is what we're looking at. This is how we're using integration by parts. It's actually a really, really nice technique. So let's look at part B. When we're looking at part B, now I want to analyze the integral of the natural log of the square root of x dx. Oops. As such. All right, let's go through that process. So again, there's not much that I can grab here for my substitution if I wanted to make a substitution. So that's kind of out of the realm of possibilities. So substitution doesn't work here. Well then, if substitution doesn't work, my next common analysis is going to be to use integration by parts, which means I need to use a u substitution. But notice there's only one piece here for a function. So that's what I'm going to use as my function choice. Natural log, and just for simplicity, I'm going to write the square root of x as x to the power of 1/2. I'm using its equivalent form. And then dv will be what's left over. Well, what's left over? Well, that's a differential dx. Okay, that's not too bad. Now, you're gonna say, okay, well, I then have to take the derivative of my substitution for u. Okay, that's fine. We know how to take the derivative of natural log of x to the power of 1/2. You're also going to have to find the antiderivative for that differential dv, in this case dx. In other words, the antiderivative for a constant with respect to x. Okay, that one's actually really straightforward, so that one's not too bad. That one we can actually find right now. Finding the antiderivative here, well, that means that v must be equal to x, because when we take this differential, we get dv is equal to dx. So again, remember I said that one wasn't too bad, and here we are. So that's the antiderivative. Now let's work on taking the derivative for u. That one's going to be a little bit more complex. All right, so what we're going to have for the derivative for u, well, we're going to have natural log, that differentiation. That's going to leave me with 1 over x to the power of 1/2, so 1 over square root of x, multiplied by the derivative of the inside. The derivative of the inside is going to be dropping the exponent forward, that's 1/2, multiplied by, dropping the exponent forward and then subtracting 1 from the exponent, and 1/2 minus 1 should get us -1/2, which means we're going to get 1 over 2 times square root of x. But multiplying these two here, we get that du is going to be 1 over 2 times x, and that's going to be dx. All right, so we still needed that small differential here. Now all we need to do to identify this, or to evaluate, we're going to take u times v minus the integral of v du. So let's work this out. The integral of the natural log of the square root of x dx is u times v, so I'm going to take my u value, that's the natural log of the square root of x, so that's u multiplied by v, which is just x, minus the integral of v du. So the integral now of v, that's just x, multiplied by du, which is 1 over 2x dx. Okay, that's not too bad. My apologies if I say that a lot. Okay, so again, I'm going to identify this is u. So u times v minus the integral of v, and then we have du. Again, integration by parts. So this naturally gets us x times natural log of the square root of x minus x times 1 divided by 2 over x. The x's are going to cancel which means we're just left with the integral of 1 over 2 dx. Well, how do we integrate that? It's a constant being integrated, which means we got x times the natural log of the square root of x minus 1/2 x. And then this is a indefinite integral, so we need plus a constant. There you are. There's your integration by parts. Again, looking at this and working with this, you have to be flexible in identifying what values you're going to want your u and your dv to be. And in a sense, those are some of the hardest aspects to actually select. All right. So now that we have this, let's go on to a different example. So let's go on to part C. Working with part C, I'm going to have the integral of e to the power of negative theta multiplied by cosine of 2 theta, and this is d theta. So again, you're going to see that substitution doesn't work too well here. So substitution is not going to work well, so we want to stay away from substitution. So in that particular instance, we more than likely want to go with this whole process for integration by parts. So I'm going to choose my u. Let's say u is equal to e to the power of negative theta. Okay, I'll be able to take the derivative of that. That shouldn't be too difficult there. My dv will then be the remainder, which is cosine of 2 theta d theta. Now I need to find the antiderivative for dv. So my antiderivative for dv, that's going to be 1 over 2 times sine of 2 theta. That should be my antiderivative. Great. Now if I want to take my derivative for u, then taking my derivative du for this function here, well, the derivative of e to the negative theta is going to be itself multiplied by the chain rule. So multiplying that derivative by the chain rule gets us negative e to the power of negative theta d theta. Now we can take the u times v minus the integral of v to u. And I should mention that when you're working with integration by parts, the second integral that we get when we set up integration by parts, meaning the u times v minus, and this is the integral I'm talking about, integral of v du, that integral we should be able to evaluate if we did this correctly. If we cannot evaluate it, we then need to go back into our techniques. Is it a u substitution that can help? Or is it another by parts? So let's see. Here we have, again, that we have this integral of e to the power of negative theta times cosine of 2 theta d theta. I need to go with u times v. So my u value is e to the negative theta times v, which is 1/2 times sine of 2 theta. So there's my u times v minus the integral of v du. So v, once again, 1/2 sine of 2 theta times du, which is negative e to the negative theta d theta. Okay, let's simplify this just a little bit more. And I'll simplify it in just a little bit. I want to keep identifying this is my u, this is my v, minus the integral, once again, of v du. Okay, so let's keep going and simplifying here. So this is 1/2 e to the negative theta times sine of 2 theta negative and negative, that's going to be a plus. 1/2 is a constant, so that 1/2 stays out in the front, multiplied by the integral of e to the negative theta multiplied by sine of 2 theta, d theta. Okay. Now, you're going to see here, well, we're almost back at the starting point, so that's kind of rough. That's kind of rough to see. But in this instance, it's actually kind of good to see that, because we know a thing or two about sine and cosine. Sine and cosine, we can keep taking those derivatives, and they're going to keep cycling through their different options. Derivative of cosine is negative sine. Derivative of sine is cosine. And again, they're going to keep cycling through, which means if I try to do one more integration by parts, then this should cycle through back to the beginning. Or at least I hope it should cycle through back to the beginning. Just by making this analysis, I want to keep going. Okay, so let's go ahead and let's keep going. Now, since we already used our u times v minus the integral of v to u, we already used our u's and our v's to make our substitutions. So instead, we're going to use different variables now. Okay, so we don't want u and we don't want v. We could go with s, but we have a function, sine, that includes an s. So I kind of want to stay away from s. Okay, so we have thetas, and I see that we possibly can use x's and y's. So let's go ahead and let's use x's and y's as part of our substitutions. Okay, so what I want now for this integration by parts, and I'm going to highlight this, that way we make sure that we're not confused, or I'm going to try to cut down on that confusion. Okay, so this initial by parts that we were using here was for the initial by parts formula that was given at the very beginning here. Now I am going to be using a different by parts formula, and I'm going to be using that by parts formula for this function here. All right. So let's go with that function there. I'm going to need to make, again, my substitutions. So let's go through some of those substitutions. I'm going to call this, let's say, x. So x is going to be equal to e to the power of negative theta. And therefore, when I take my dx, I will get negative e to the negative theta d theta. I'm going to choose my dv as everything else, or in this case, my dy as everything else in that integrand, which is sine of 2 theta d theta. And finding my antiderivative for this dy will then give me that y is equal to negative 1/2 cosine of 2 theta, and this is my antiderivative. And again, this work here is done for this integration by parts that we have here on this line that we're working with on the right-hand side of your screen. So in order to finish this off, we're going to keep going. We still have this first term, 1/2 e to the power of negative theta times sine of 2 theta plus, remember, we still have this 1/2 out in the front of this integral, so 1/2 multiplied by u times v minus the integral of v du. In this case, it's x times y. Okay, so we're going to go with that x times y. So that's e to the power of negative theta times negative 1/2 cosine of 2 theta minus the integral of v du, in this case, y times dx, and that's going to be negative 1/2 cosine of 2 theta multiplied by negative e to the negative theta d theta. And here we are. Now, again, I'm going to highlight this, that we're initially looking at this initial piece, which was my x value, so x times y, and this is the equivalent of u times v minus the integral of v du. So what was our v component in this particular case? Well, that v component was just y times the integral of du, where du in this case was my dx. And so using this, I can now, again, simplify just a little bit more. And so now we have 1/2 e to the power of negative theta times sine of 2 theta plus, let's distribute this half into this whole mix. Okay, so distributing that half, so this is actually going to turn into a minus because we have a negative here. So minus 1/4 e to the power of negative theta multiplied by cosine of 2 theta. I have a negative, and another negative. So negative times a negative is positive, times another negative is a negative again. So we're left with negative. Remember, I have a coefficient of 1/2, but then I'm distributing another coefficient of 1/2, which means I have 1/4 multiplied by the integral of e to the power of negative theta times cosine of 2 theta. And that's d theta. Now remember, this is all equal to this initial to this initial integral. So all of this is equal to integral of e to the negative theta multiplied by cosine of 2 theta d theta. Now, I wanted to do this for this specific reason, that if you look at this particular integral, e to the power, the integral that we started with, that integral actually appears on the right-hand side, which then means that we can combine those integrals. And I forgot to highlight this piece over here. My apologies. That's that integration by parts. Okay, so let's keep going. Let's get all of the like integrals on one side. So if I get all of the like integrals on one side, and I'm going to move this down here, I now have the integral of e to the negative theta multiplied by cosine of 2 theta d theta plus this integral that I'm adding to the other side, which is 1/4 multiplied by the integral of e to the negative theta times cosine of 2 theta d theta, is going to be equal to 1/2 e to the negative theta times sine of 2 theta minus 1/4 e to the power of negative theta times cosine of 2 theta. Just like this. So look at the left-hand side now. We have like terms. So let's go ahead and let's add those like terms. Well, 1/4 plus 1, that should get us 5/4. So on the left-hand side, we have 5/4 of the integral of e to the power of negative theta multiplied by cosine of 2 theta d theta. On the right-hand side, we still have all of these terms. So we have 1/2 e to the negative theta sine of 2 theta minus 1/4 e to the negative theta times cosine of 2 theta. And look at that. At the very beginning, what we were trying to do is we were trying to solve, or we were trying to integrate e to the negative theta times cosine of 2 theta. And we actually almost got it done, because look at this last line that we're on. This last line on the left-hand side has the integral that we were initially solving for. The right-hand side no longer has that integral. All we have to do here is isolate that integral, which means we're going to multiply by the inverse of, or the reciprocal of 5/4. So e to the power of negative theta multiplied by cosine of 2 theta d theta, well, let's multiply by 4/5, If we multiply by 4/5, then we're going to be left with 4/5 multiplied by 1/2 e to the negative theta sine of 2 theta minus 1/4 e to the negative theta times cosine of 2 theta. All right, we're almost there. Let's finish this off. E to the negative theta times cosine of 2 theta d theta. Distribute. We now get 2/5 e to the power of negative theta times sine of 2 theta. Again, distribute. We get negative 1/5 e to the negative theta times cosine of 2 theta. And what type of integral was this, or is this? This is an indefinite integral, which means we need plus c. And there you are. Easy peasy. Check that out. That is amazing. That is some beautiful work right there, if I do say so myself. Now, these types of integrals, again, you have to make sure that when you're taking these types of integrals, you are ready to make sure that you are prepared to possibly cycle through maybe a few iterations of by parts. As soon as you tackle that on, it's my firm belief that you will be able to extract all of these values, and it should be somewhat straightforward from there. Great. So let's keep working. I now want to work on part D. Or you know what, let's make this a new example. I like a new example here. So let's go ahead and let's make this a new example. We want to evaluate the integrals. Part A. We're going to evaluate the integral from 0 to 1 for the quantity of x squared plus 1 times e to the power of negative x dx. And again, we could possibly try substitution and see where that leads us, but you can try to figure out that substitution won't work directly here. So if that's going to be the case, let's not use substitution, and let's go with the whole integration techniques that we're learning in this section, which is by parts. Which means I need to make a u substitution. So I need a u, and that is going to be, let's say, x squared plus 1. Okay, taking that derivative, or that differential, du is going to be 2x dx. Whatever's left over, which is my dv, is going to be e to the negative x dx. Finding the antiderivative here will be negative e to the negative x. Again, here is my antiderivative. Okay, great. So what I have now is that I'm looking at my integral from 0 to 1, and this is going to be x squared plus 1 times e to the power of negative x dx. I'm going to take my u and v, so u times v. All right, so taking my u times v. All right, let's actually write this out. There we go. Taking my u times v, that's going to be x squared plus 1 multiplied by v, which is negative e to the negative x. Now I'm going to stop right here, because since I have limits of integration, I need to evaluate that specific term for those limits of integration. And then I carry on minus the integral, keep the same bounds, because we're not changing variables. We're only using the substitution, or in this case the by parts, in order to break this integral up and keep going with the exact same variables. So minus the integral of the integral from 0 to 1, and this is going to be the integral of v du. So v in this case is negative e to the negative x, and then du is going to be 2x dx. Okay, we can keep going. Now, let's evaluate this first term here. So this first term, we want to evaluate from the interval from 0 to 1. So we're going to go ahead and do that. So this is going to be 1 squared plus 1 multiplied by e to the power of negative 1 minus 0 squared plus 1 times negative e to the power of negative 0. There we are. And so again, this first piece, when we wanted to evaluate that first piece is right in here. Great. Let's clean up the second piece. Negative times a negative is positive, and then we're going to factor out a 2. So that's going to be plus 2 times the integral from 0 to 1 for x times e to the power of negative x dx. Okay, looking pretty good there. So look at that second integral. That integral from 0 to 1 for x times e to the power of negative x dx. That integral, we're going to have to go ahead and integrate that, but we can't integrate it with our techniques for substitution, which means we're going to have to use, once again, this whole process by parts. Now, in order to do this, what I'm going to do is I'm going to clean up this first term that we had here. All right, so let's go through and let's clean up this first term. 1 plus 1, that's going to be 2, so that's going to be negative 2 e to the power of negative 1. All right, and then we have a negative here, another negative, so it's going to be a positive, plus e to the power of negative 0, that's still going to be 1, so we have 1 times 1, which is just 1. Great. And then we still have plus 2 times the integral from 0 to 1 for x e to the negative x dx. Okay, here we are. Now, again, we have to go with this by parts once again. And in doing this by parts once again, we now have to select two different variables that we're not going to be using as we move forward. So I could choose R and S. I guess that would be good. Okay, so here we go. I'm going to choose R is equal to, I'm going to say X in this case, and therefore when I take the derivative, dr, this is going to get me dx. Whatever remains is that dv, so dv is equal to, or you know what, I'm not using v. I'm going to use ds is equal to e to the power of negative x dx. Finding this antiderivative will get me that s is equal to negative e to the negative x. And that's my antiderivative. So here is my antiderivative. Now, in doing so, I'm going to come back over here. Now, remember that for the very first term, we've already evaluated, so we don't need to do anything else with that. So that's just going to carry down. There we are. Plus 2 times this integral. So again, that integral is at u times v minus the integral of v du. With our substitutions here, it's going to be r times s minus the integral of s times dr. Now, this is why I always set these integrals, by parts integrals, in this specific manner, where I always identify what is my u, what is my dv, and then I find the derivative going downward, find the antiderivative going upward. Setting them up in this manner will make sure that regardless of whether you're using u's and v's, then you're always going to make sure that you have your integration by parts set up correctly if you use this technique. So now that I have this, then this is going to be my u times v, in this case r times s, is going to be negative x e to the negative x minus, and this is evaluated from 0 to 1. So evaluated from 0 to 1 minus the integral from 0 to 1, and this is going to be for negative e to the negative x multiplied by dx. There we are, looking nice. That last integral we can definitely do. So let's keep going. Negative 2 e to the negative 1 plus 1 plus 2, and this is going to distribute now. So let's go ahead and distribute. So we're going to have negative 2. So 2 times negative x. So this is going to be negative 2xe. Or you know what? I actually want to evaluate from 0 to 1 first before I distribute. My apologies. So evaluating here, that's going to be negative 1 multiplied by e to the power of negative 1 minus, once again we still have that negative x. In this case it's going to be negative 0 multiplied by e to the power of negative 0. All right, that's that first piece. Negative times a negative, that's going to be a positive, so that's positive for the integral from 0 to 1 for e to the power of negative x dx. Looking pretty good. I'm rewriting here, so notice this second term, since it's being multiplied by 0, this is automatically going to just cancel out, which means my first term here, negative times a negative, is going to be a positive. And oh, Cheetos. I accidentally did one too many negatives there. Okay, so my apologies there. So in here I get negative, there we go, that's where the negative comes into play. Negative 2e to the power of negative 1. Awesome. Let's keep going. All right, looking good so far. And then we're going to evaluate over here on the right-hand side, distributing that 2. So we still got that 2 distributed, and that's going to be 2 times this integral, e to the negative x. That integral is going to be negative e to the negative x evaluated from 0 to 1. Okay, well, that's pretty good. So let's keep going with this. Negative 2e to the power of negative 1 plus 1 minus 2e to the negative 1. Oh, look at that. E to the negative 1 has 2 coefficients already, so that's negative 4 e to the negative 1 plus 1, and then we have this coefficient here, so that's going to be plus 2 times negative e to the power of negative 1 plus e to the power of negative 0. Ooh, look at that. That is awesome. Negative 4 e to the negative 1 plus 1 plus, or in this case minus 2 e to the negative 1. Distribute that and we get plus 2, which means final answer here, everybody, negative 6 e to the negative 1 plus 3. Ooh, wowzers. Check that out. Man, oh man, oh man. That was beautiful. That was awesome. I love that. So now that we have this, again, we can now keep working with this integration by parts, and we have to keep using our techniques that we've been developing through these past few semesters in calculus. Awesome. Now, let's see if we can work with another example, and I'm going to call this example part B. Now, for this example, let's see what I'm going to want here. This is going to be the example for the integral from 1 to the square root of 3 for arctan of 1 over x dx. Okay. Nice. So remember, arctan arctangent of, let's call it theta, is equal to tangent inverse of theta. It's just a different way to write it. So try not to let that confuse you too much. So we know that we're looking at some tan inverse. And just by looking at this integral, it doesn't seem that we can integrate this directly, which means we're going to have to integrate this using by parts because the substitution will not work. So again, my same setup, which I'm going to say that u is going to be my whole function, which will say it's arctan of 1 over x. That means my du will be 1 over, or in this case a derivative, 1 over 1 plus 1 over x squared, because again we're squaring this term, multiplied by the derivative of the inside function. So the derivative of the inside function, this is going to be negative 1 over x squared. All right, that's looking pretty all right so far. And that's dx. My dv is going to be my dx, whatever was left over on that integrand, which means my v is equal to just x. Let's clean up my du. My du can look like it needs to be cleaned up. I get negative 1 divided by distribute the x squared. That's going to be x squared plus 1. There we are. Doesn't look too bad. And again, that's dx. Okay, so we take our u times v, and then we subtract out the integral of v du. So let's go with it. Integrating from 1 to the square root of 3 for arctan of 1 over x dx. This is going to be the integral of u times v. So this is going to be arctan of 1 over x multiplied by x. So again, u times v minus the integral. Bounds from 1 to 3, from square root of 3. Bounds for the integral, 1 to square root of 3. And this is going to be minus the integral v du. So v du is going to be negative x over x squared plus 1 dx. All right, that looks pretty good. Let's keep going. Let's evaluate this first term. So evaluating the first term, we're going to get arctangent of 1 over square root of 3 and multiplied by x. So let's actually multiply the x out in the front is what I prefer here. There we go. So square root of 3 multiplied by arctan of 1 over root 3 minus 1 times arctan of 1. All right, that's looking good. Negative and negative, that's going to be a positive. And so that's going to be plus the integral from 1 to the square root of 3 for x divided by x squared plus 1 dx. Wow, that's looking very good. That's looking very promising for us. Okay, so one of the first things that we are going to have to do in this case is that we are going to need to find what is arctan of the square root of 3. So in other words, we need to find where this tan inverse gets us an angle whose ratio is 1 over root 3. Well, remember, tangent is bounded, or in this case, the outputs for tan inverse are bounded between negative pi halves and pi halves, non-inclusive on the pi halves. This particular answer for arctan, this is going to be the ratio, or sorry, the angle measurement of pi 6. Pi 6, in other words, 30 degrees, should get us that ratio for tangent to be 1 over root 3. Minus what ratio for tangent gets us 1? Well, that's 45 degrees, which means it's pi fourths. So that's minus pi fourths. There we are. That's looking good. Plus, this next integral, what we're going to do for that integral is we can actually use a u substitution there. All right, so we can go with a u substitution for that particular integral. So we don't need by parts here. We just need a u substitution. But since we already used the variable u and the variable v, let's use something else. So I'm going to use my variable, I don't know, let's say y. So I'm going to say y is equal to x squared plus 1. This means that dy is going to be 2x dx, which means 1/2 dy is going to be equal to x dx. All right, that's looking good. So then this is the integral, x dx, that now turns into 1/2 dy. And then this turns into 1 over y multiplied by 1/2 dy. Now my bounds. Well, for my bounds, I have that x is equal to 1, so that's one of the first bounds that I need. Okay, so let's work on that when x is equal to 1. So x is equal to 1, what is this going to tell me about my y values? Well, this tells me that my y values of x is 1. that my y values are 2, which means for my lower limit of integration, for that 1, we get a lower bound of 2. Now, upper bound, x is equal to the square root of 3. What happens to my y value, that substitution that we made, if we use square root of 3 into that function? Well, square root of 3 squared is just 3. 3 plus 1 is 4, which means my upper bound is 4. So we fixed our bounds for integration. That way we don't have to go back and resubstitute. Okay, so that's nice. So this is root 3 pi divided by 6 minus pi fourths. I have a constant here, so that's going to be plus 1/2. And this is now going to be the integral from 2 to 4 of 1 over y dy. The integral for 1 over y, or 1 over that variable, is just going to be the natural log of the absolute value of that variable, which means this is going to evaluate to the natural log of the absolute value of y, evaluated from 2 to 4. We go through that substitution process. Alright, so this is then going to be 1/2 multiplied by natural log. Since the interval from 2 to 4 is always positive, I can drop the absolute values, and this will be 1/2 multiplied by natural log of 4 minus 1/2 multiplied by the natural log of 2. Okay, we can condense here, so rest assured we are going to condense. Let's get some common denominators here for these pi's. Okay, common denominators here for my pi's. Between 4 and 6, that's going to be 12. Okay, so that's going to be 2 root 3 minus, this is going to be 3, all divided by 12, and this is multiplied by pi. Now, I have a half here, so I'm going to have plus 1/2 multiplied by the natural log. Remember, if I factor out a half, I now have the natural log of 4 minus natural log of 2. Same natural logs subtracting one another. That means we can divide their arguments, which means it's the natural log of 2. Simplify just a little bit further. Oops. Plus the natural log of the square root of dos. And here is the answer. Ooh, my goodness. Look at that. Isn't that just beautiful, elegant, and awesome? Oops, I forgot the pi. Oh my goodness. And there we are. Perfect. Wow. That is amazing. Love that. Awesome. So this now wraps up our whole section for this integration by parts. Now again, integration by parts, I highly, highly recommend that you take some time, that you take a lot of time, and you familiarize yourself with how to identify these by part integration integrals. You want to always make sure that you try U substitution first. If a U substitution does not work, then try by parts. All right. So again, pay close attention to how you're evaluating these and what approaches you're taking. And if you all have any questions, again, please feel free to stop on by my office hours, and I will be more than happy to help you out. I hope that you all enjoyed this lesson, and I will see you all next time.